Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this particular video, we're going to talk about local linearity, also known as tangent line approximation. Let's find out. The idea of local linearity actually comes from this perception that, this curve, if you were to zoom into a particular point, several times, like 1,000 times magnification or even more than that, if you actually zoom in several times into any curve, then any curve actually looks like a line, right? It's very small. I'm talking at a very small region. If you just, zoom in several thousand times, several million times perhaps, that curve in that region will actually be, almost like a straight line, just that piece. So if you were to draw a tangent at that point, let me just draw the axis first. Okay, so if you have the y-axis and the x-axis, something like this. Okay, and if you were to try and consider a tangent at that point, I should use another color for this. Let's draw a straight line, a tangent line at that point. Let me see how well I can do this. So there you go. Now that's a tangent line. Okay, so the idea is that at that point, so let's say that this is the point A. And of course, at that point, you have the value of the function. The value of the function at that point should be f of A, right? And let's just, for the sake of convention, let's just call this tangent, the equation of the tangent is Tx. The function is f of x, the tangent is Tx. And we're looking at that point A. We know that that point A, f of A, the value of the function at the point A and the value of the tangent T of A will be the same, all right? So let me just write that thing down. F of A is going to be equal to T of A. All right, you could have written it with a small letter t, but that's okay. But that literally means that that point is common, tangent, right? That's one idea we're going to use on this. The second idea is that suppose you didn't know the function, or it might be a very complicated function. We didn't have any kind of calculators, but now we can, all kinds of calculators, we can find the value. But this technique was used only when the calculators are not available. All these fancy calculators came much later on. So perhaps you may not have that kind of appreciation for this particular technique. But remember, this technique was used along with other techniques like Newton's method, approximation using Taylor polynomials. All those techniques were used when the calculator was not even invented. Okay, so the idea is that we are trying to find the value of a function very close to A. So let's say there was another point, something like A plus H, very, very close, okay? A plus H on the x-axis. Its corresponding value on the curve. Suppose we did not know, it was very difficult to find. This is what we're talking about. So its corresponding value is on the curve. The idea of local linearization is that we can make use of the equation of the tangent. We make use of the equation of the tangent to evaluate or to approximate. So we find A plus H using the equation of the tangent because that's a linear equation. And using that, we will approximate the value of the function. Sounds strange to you? Well, remember, this is an approximation technique. Okay, so what's happening is if I were to zoom in several times, okay, so let's say this is the line that was tangent, and let's say this is the curve, right? There's a curve, and we're looking at this point out here. Okay, so that's our f of A, also T of A, and there's some other point here. Let's use another color. There's some other point here. Now this is zoomed in, therefore it looks like a larger gap, okay? And it's corresponding. So this is, let's use another color. The x value, okay, that x value should be something like A plus H, okay? Close by. I'm saying close by, I'll explain why. Okay, so we've zoomed in quite a bit. So this value, the value of the function here should be f of A plus H, right? But the corresponding value at A plus H for this tangent, this is the point here, okay? Because it's on the tangent, would be T of A plus H. And clearly you can see that, T of A plus H is here, whereas f of A plus H is there. Clearly there's a gap, there's going to be an error. But as long as you choose those points close enough to A, close enough to the point of tangency, remember A is where, they both agree, as we said, f of A is equal to T of A. But if you choose it closer to A, obviously if you choose further away, let's say that was something like A plus 2H, okay? depending upon the value of h. This would be the value, okay? This would be t of a plus 2h. And if the function, goes somewhere like that, then the corresponding value around a plus h for the function would be somewhere there, right? Can you see the error so much more now? Can you see that? That is the amount of error. And that's because of how far away it is from a plus h, okay? This is a hypothetical situation. We'll take a look at it in an actual situation right now. But the idea of approximating using a tangent line is that as long as the point, the values a plus h, the value of a plus h is close enough to a, as close as possible to that point of tangent c, we can use the tangent line to approximate the value of a function which is close enough. So it could have been even on the left-hand side of a, all right, something like a minus h, but remember it has to be close enough to the point of tangent c. Then it'll be a better approximation, okay? But it comes from this idea, like I said, the perception that a curve, any curve, if you zoom in many times, many million times perhaps, if you're not satisfied 1,000 times, okay? If you zoom in many times, any curve is actually a piece of a straight line. And from using that idea, because of just that small region being a straight line, we are taking into account an approximation that's close enough to a. So basically, what are we doing? We are finding the equation of the tangent and using the equation of the tangent. This is t of a plus h. Using the equation of the tangent, we are approximating values of the function close enough to that point of tangents. Cool. That point is sometimes known as the base point, but that's just terminology. Here's another thing, okay? If there's a curve that's concave up, this shape is called concave up, and we'll talk about concavity in some other video because that's when we will be talking about the second derivative and the behavior of the function. So this is just the shape, so we are just going to call this concave up, okay? This is concave up. A parabola that's U-shaped is known as concave up. And likewise, a parabola that's inverted U, we're going to call it concave down. Right? Now, if you were to draw a tangent to a curve that is concave up, let me just show that to you, right? So if I just draw a tangent, and if you're using local linearity, and remember what local linearity is, that this is the point of tangent C. This is the point where the equation of the tangent and the equation of the function, the function, they would agree at that point, right? But if you take a point that is close enough to approximate, so here's the point, let's say that was along the x-axis, here's the point, all right? So that is our a plus h, and that's our a. This is the point on the tangent, and this is the point that we are approximating. And let's just assume that this is close enough, okay? Because this is, we can't zoom in. I just made it a little wider so that we can see what values we're looking at. So this is the value here on the function, and the corresponding value on the tangent. Let's mark it with, what color can we go? Maybe the same color, all right? Or maybe a different color, let's say. That's the value on the tangent, okay? Now, you can see that because it's below, it's going to be what we call an underestimate. Underestimate. How do we spell that? Okay, one sec. Let me try it again. It is underestimate. Underestimate means it's going to be lower than the actual value. You can see that the graph of the function is above the tangent, and that's because it's concave up. Likewise, if the same case were a concave down and you were looking at a tangent, all right, at a point here, okay, and you draw a tangent here, and you're using the same technique of local linearity, which means we're using the equation of the tangent to approximate the value of the function, then it's going to be an overestimate because corresponding values, this time I'm taking the a minus h, okay? So let's say that was the axis, and this is our point A where they agree, and let's say this is close enough, but on the left-hand side, as possible, a minus h, okay? Its value on the curve will be below the tangent, and because it's below, it's going to be, and the point we're using is this one to approximate, right? So it's an overestimate in this case, overestimate. So this is a process of estimating the value of the function using the tangent, all right? So that's why it's called tangent line approximation. And because in a concave down scenario, the tangent is above that curve, it's an overestimate. You're using the tangent line to approximate. Here, the tangent is below the curve in a concave up. It's going to be an underestimate. Clear? Now let's try and take a look at an example. All right, here the function is not given. All right, can you read the question? Okay, it says f is concave up. So they've given you the information that the function is concave up. Clearly, it's going to be underestimate, okay? I already explained that, okay? So if the function is concave up, it says it's concave up on its domain, and they've given you some information. F of 4 is equal to 5. In clear terms, f of 4 is equal to 5 literally means you're talking about a point with coordinates x is equal to 4, x is equal to 4, and y is equal to 5. That is what this f is equal to, f for 4 is equal to 5 literally means, okay? X equals 4, y equal to 5. And they've given another information that f prime at 4 is 3. Okay, that's also important information. That means that the slope of the tangent at x is equal to 4, if that's the base point, the slope of the tangent at x equals 4 is going to be 3. Okay, we've already seen the meaning of the derivative, the first derivative, that is, okay, the slope of the tangent at the base point x is equal to 4 is 3. What else have they given, asked in this question? They've asked, what is the estimate of f of 3.8? If you can't read the question because of all my coloring, here you go, f of 3.8. So they asked, what is f 3.8? As you can see, our base point is 4. 3.8 is slightly on the left hand side, right? We can approximate. What is an estimate for 3.8, f of 3.8, using the local linear approximation for f at x is equal to 4? That becomes your base point. That becomes the point where we are looking at the tangent C. That's the A. All right, so we're looking at something like this, a minus h. It's a concave up. Okay, so all that we need to do is that we need to find the equation of the tangent line. Using the equation of the tangent line, we are going to find an approximation for f of 3.8. Clear? So what do? We've got the slope of the tangent line. We've got the point where we need to find the equation using point slope form again. So the equation of the tangent, if I have to write it here, equation of tangent at x is equal to 4 is going to be y minus y1 is equal to m, which is 3, times x minus x1, which is 4. Now, sometimes this form is good enough, especially when you are trying to approximate, okay? But sometimes you might just want to write it down in a simplified form and then find the value. That's also okay. So sometimes I'll do an example where this is easier, okay? So let's see. This becomes, when you simplify, y is equal to 3x minus 12 plus a 5. And the equation of the tangent we have is y is equal to 3x minus 7. This is the equation of the tangent. And what we are trying to do is we're using the equation of the tangent to approximate the value of the function. All right, so let me just write that thing here. If equation of the tangent is t of x is basically 3x minus 7. So t at 3.8 is what we're trying to find out. T at 3.8, okay? And again, we have to jump to the calculator for this kind of thing, all right? But we'll try and do it without the calculator. It's a simple multiplication. 3 times 3.8 minus 7. 3 and 8 is 24. 3 and 3, 9 and 11. So it's 11.8 minus 7, giving you the value is 4.4. This is t of 3.8. And we say that f at 3.8 is approximately equal to 4.4 using the tangent line approximation. So using the equation of the tangent to find the value of the function close enough to that base point 4. Okay. If you found this video useful, make sure you like, share, and subscribe to this channel. I'm going to see you all in the next video.